तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In this lecture, we will begin a new topic, namely the bipolar junction transistor. This is the 26th lecture of the course. In the first 18 lectures of this course, we have discussed the basics of semiconductors. Then in next 7 lectures, we discuss the basics of p-n junction. We are now ready to consider the various transistors. First, we will consider the bipolar junction transistor. Let us see what characteristics we are going to explain for this device. First, we will explain the common emitter output characteristics. Let us first understand what is meant by common emitter. Here we see the biasing arrangement in which the characteristics are measured. As you know, the transistor has 3 terminals, unlike the diode which has 2 terminals. In fact, the transistor contains 2 p-n junctions back to back having a common region. So for example, a PNP transistor will consist of an n region on the either side of which you have 2 p regions. The n region will be very thin, so the 2 p-n junctions are in a very close proximity. The reason for the 2 junctions to be maintained in close proximity will become clear when we discuss the transistor action. So now let us look at the symbol of a PNP transistor. So here you have the emitter junction showed by this arrow. So P region is emitter and N region is the base. So P-N junction. The arrow shows the emitter junction. Similarly, you have the collector. This is the collector. This is again made of p-type material. So P, N, P. That is the arrangement. P-type collector, N-type base and P-type emitter. Now what we mean by common emitter is that the voltages which are applied, either the voltage or the current, the sources are applied with emitter as the common terminal. So you can see here that you are connecting a base current with reference to the emitter, and similarly you are applying a voltage to the collector with reference to the emitter. Now what you find is that the collector for a PNP transistor is negative as compared to the emitter in this arrangement. Similarly, the base current is flowing out of the base terminal, and finally the collector current is flowing out of the collector terminal. The polarities will be reversed for an NPN transistor. Now this collector side is referred to as the output side and the base side, that is this side, is referred to as the input side. So when we talk of output characteristics, we are really plotting the collector current as a function of the collector to emitter voltage, which is varied. Now when we plot this kind of characteristics, we maintain the base current constant. Then we change the base current to a new value, and maintaining it constant we vary the collector emitter voltage and see how the collector current varies for the new base current condition. Now when we do this exercise, the resulting characteristics which are called the output characteristics, will look something like this. So here you can see the collector current is plotted as a function of collector to emitter voltage. Both the collector current and collector to emitter voltage are negative. Now it is clear that the collector to emitter voltage is negative because collector is negative with respect to emitter. The reason why collector current is also shown in negative quantities is because the convention is that when a current flows out of a terminal, then it is regarded as negative, whereas if a current flows into the terminal, it is regarded as positive. The collector current, as you see from the biasing arrangement here, is flowing out of the collector terminal. Let us also understand the order of magnitudes of the quantities. The base current is small and it is of the order of tens of microamperes. The collector current, on the other hand, is of the order of milliamperes. So the collector current is more than 100 times the base current. For instance, for a base current of 36 microamperes, your collector current is of the order of 3.6 milliamperes. Okay? So there is a factor of 100 difference between the two. Now the collector to emitter voltage is, you can see, of the order of few tens of volts. Let us look at the characteristics in greater detail. What is happening when you sweep the collector to emitter voltage, base current maintained constant? Let us take a specific case. For example, let us again take the 36 microampere base current case, that is this. When we sweep the collector to emitter voltage from 0, we find that in a fraction of a volt the collector current is rising, and beyond this point the rate of rise of the current reduces drastically, or we can say the characteristics tend to almost saturate. They are not exactly saturating because the current is not constant, but they are almost saturating because the current is increasing at a very slow rate with respect to the voltage. Now let us define the various regions of the transistor operation on this particular graph on the output characteristics. This particular area that is hatched, which corresponds to the region below the characteristics for 0 base current. Note that when the base current is 0, there is still a small collector current. We will explain what is meant by this beta and ICO later when we discuss the characteristics in detail. The beta is simply the ratio of the collector current to the base current. So here you can see it is of the order of 100. This region, which is hatched and which is below the base current equal to 0 curve, is called the cutoff region, because the transistor really has almost no current flowing for this particular range of operation. Next, this shaded area, the blue area, light blue shaded area, where the current rises rapidly with voltage for various base currents, is referred to as the saturation region. Now this is somewhat misleading because we would like to call the region where the current is increasing slowly, that is this region, as the saturation region, because the characteristics tend to saturate. Unfortunately, for bipolar transistors, it is this light blue shaded region which is called saturation, where the current is increasing rapidly. The reason why it is called saturation will become clear, but this is the region where the collector to base terminal is forward biased. We will see this later, and we will also explain why it is called saturation. Let us identify another important region of these characteristics, and that is the breakdown region. The region to the right of this dashed line is the breakdown region. So what you find is that the characteristics for various base currents do not have the same breakdown voltage. Okay? As your base current increases, the breakdown voltage falls, at least in this region, where the collector current is of the order of milliamperes. The breakdown voltage corresponding to base current equal to 0 is the maximum breakdown voltage that this transistor can have in the particular biasing arrangement. So this breakdown voltage is referred to as VCEO, that is the maximum collector to emitter voltage. CE stands for collector to emitter voltage, and O stands for base open. Since the base current is 0, it means that the base terminal is open. So this is called the VVCEO rating, okay, the breakdown voltage rating of the transistor in the common emitter biasing arrangement. This is a very important parameter for a bipolar transistor. Now, having identified the saturation, cutoff and the breakdown regions, we now come to the very important region in which most of the transistors operate. That is the remaining region on this particular graph, that is this region in between the cutoff, saturation and breakdown, and this is called the active region of the transistor. The transistor operates in this region in most of the situations. In fact, this is the useful region of operation. Now, having seen the output characteristics, let us see the input characteristics of the transistor in this arrangement. Since the base side is the input side, the input characteristics would mean the variation of the base to emitter voltage. Note that the emitter is positive with respect to base. So emitter base junction is forward biased. So VBE is negative because base is negative with respect to emitter. So variation of VBE with IB for a given collector to emitter voltage. This is the so called input characteristics. So they look something like this. These are diode like characteristics. The reason is very simple. Since this is a diode, the emitter current, the current flowing through this diode is the emitter current. The current through this lead will always be exponentially related to the voltage across the diode. Now, as we have seen in the output characteristics, the collector current is much larger than the base current. The collector current was of the order of milliamps, whereas the base current was of the order of tens of microamps. So there is a factor of 100 difference between the collector and base currents. So by Kirchhoff's law, the collector current would be almost equal to the emitter current, because the base current is 100 times smaller than this, and sum of all the current should be 0. So that is why there is a constant factor between the base current and the emitter current. So emitter current is also approximately 100 times more than the base current, or told in another way, the base current is a fraction of the emitter current, and which is almost constant when the biasing voltages and currents change. So therefore, since base current is almost linearly related to the emitter current, and emitter base junction characteristics are exponential, that is the variation of base emitter voltage, or rather the variation of the emitter current with base emitter voltage is exponential. Therefore, the variation of base current with base emitter voltage will also be exponential. Okay? So that is why on this axis you have the base current, which is of the order of tens of microamps, and this is the emitter base voltage axis. You see that the characteristics show a small dispersion with respect to the collector emitter voltage. So for collector emitter voltage increasing, the curves start shifting to the right, but the shift is very, very small. So these are the input characteristics of the common emitter mode of operation. Next, we will explain the beta versus collector current characteristics. These look something like this. So you find the ratio of the collector current to the base current, which is the beta, is low for low collector currents. It increases, reaches a maximum, and again starts dropping for high collector currents. So here, since the collector current is shown over a very wide range, over orders of magnitude, the scale chosen is logarithmic. So beta versus IC characteristics will normally be shown with collector current on the logarithmic axis, and here, since the beta also is varying over a wide range, over orders of magnitude, it is shown on the logarithmic scale. The collector to emitter voltage under which these characteristics are taken is fixed, in this particular case at -2 volts. Now, having considered the active region of operation, it is also important to know the breakdown characteristics of a transistor. So collector current as a function of collector to emitter voltage shows a breakdown characteristic something like this. This is the VCEO, which we discussed already. Now if the transistor is operating in common base mode, that is the collector voltage is applied with respect to the base voltage, then your breakdown voltage is higher, and this breakdown voltage is referred to as VCBO, that is collector to base breakdown with emitter left open. So we will also explain why VCBO is much higher than VCEO. We will then explain the AC characteristics of the bipolar transistor. As in the case of p-n junction, the AC characteristics will be represented using an equivalent circuit for the transistor. This is called the small signal equivalent circuit. There are two types of equivalent circuits which are used. One type is called the H parameter model, which is what is shown here on this particular slide. So this particular model is directly derived from the DC common emitter characteristics, which are shown here, the output and the input characteristics which we considered just now. So from these characteristics you can derive the small signal equivalent circuit. Obviously, since we are deriving the equivalent circuit from DC characteristics, this equivalent circuit is valid for low frequencies. So generally the H parameter equivalent circuit is used for low frequencies. Some more justification of the use of H parameter equivalent circuit will be discussed later when we take up the characteristics in detail. Now let us see what these equivalent circuit components mean. Now this is the DC biasing arrangement for measuring the common emitter characteristics. So what we do is we superimpose a small base current on the DC current existing. As a consequence of this base current, small signal base current, you will have a small signal base emitter voltage and a small signal collector current resulting in the circuit. Now these effects, that is the variation in the base emitter voltage and the variation in the collector current in response to the variation in the base current, can be represented as follows. Between the base and emitter you put a resistance, so IB is the base current which flows through this resistance, giving rise to a small signal base to emitter voltage, that is this voltage. Similarly, the small signal collector current resulting from the base current, that is a small signal output current because of the small signal input current, can be shown as a controlled current source. So the collector current equal to base current into a multiplication factor. Now in addition, if you now superimpose a small collector emitter voltage, these collector currents and the base emitter voltages will be slightly modified. So these modifications can be represented using two additional components. So this is the collector to emitter voltage applied. Since the collector current is changing in response to this, you put a resistance here, and then since the emitter base voltage also is changing a little bit in response to VCE, this is shown by a dependent voltage source. So this voltage source is in series with the resistance that we talked about earlier, because sum of these two voltages actually represents the voltage between the base emitter terminals when you have changes in the base current and the collector emitter voltage. Now the symbols for the resistance is 1 by HOE, and for the multiplication factor, that is the relation between this voltage and the collector to emitter voltage, the ratio is HRE. So this is the small signal equivalent circuit as per the H parameter model. Generally, this voltage source which is present here is negligible, and so normally it is neglected. So the H parameter equivalent circuit used in practice has only three components: a resistance at the input, a controlled current source in parallel with the resistance at the output. Another small signal equivalent circuit which is often used, which works for both low and high frequencies, is so called hybrid pi model. The reason it is called pi is because of the shape of this particular circuit. So you can see that this arm together with this arm and this resembles the symbol pi, the shape of the symbol pi. That is why it is called hybrid pi equivalent circuit. So we will also show how this equivalent circuit can be derived. The difference between H parameter equivalent circuit and the hybrid pi circuit is that the current source between the collector and emitter is shown controlled by the base to emitter voltage rather than the base current, so that here you have, instead of beta, the parameter transconductance Gm. That is a significant difference between H parameter equivalent circuit and the hybrid pi equivalent circuit. We will consider the relative advantages and disadvantages of the two when we discuss the characteristics in detail. Now to explain these DC and small signal characteristics, we will proceed as follows. First, we will discuss an historical account of how the transistor came into being, how it was invented, under what conditions. Then we will discuss the device structure, that is the real structure, and that structure, that is the simplified structure that we will use for the purpose of our analysis. Then we will discuss the basics of transistor action. In this, first we will consider the current transfer from forward biased emitter junction to zero biased collector junction. So these two junctions are in close proximity. One of them is forward biased and the other is zero biased. There is no bias across the other junction. Then how the current is transferred from forward bias to zero bias junction. Then we will discuss the effects of DC bias across the collector junction. If you change the collector junction from zero bias to DC bias, what happens? With this, we will be ready to discuss the small signal amplification using bipolar junction transistor. The small signal amplification is the most important application of this transistor action. Then we will consider the common emitter current voltage characteristics. We will explain how the various features of the characteristics arise. And finally, we will consider the small signal equivalent circuits. That is, after considering the DC characteristics, current voltage characteristics, we will consider the AC characteristics, and the result of this will be in the form of an equivalent circuit for the bipolar transistor that we have already shown. So now let us proceed with the history of the device. During the 1920s, when a lot of research work was going on semiconductors, an idea was floated, and that is, why not we make a vacuum tube triode like structure in semiconductors. See, this is the idea of the solid state triode. So the vacuum tube triode was being used for amplification. It was a device made using vacuum tubes in which there were 3 terminals. Immediately when people started working on this idea, 2 patents were filed. So these are illustrated here. One was by Lilienfeld in 1925 and another by Heal in 1935. The basic ideas in these patents were the same and are illustrated using this diagram. So the idea was as follows. So you have a semiconductor block whose resistivity is sought to be modulated by a metal electrode which is placed in close proximity to the semiconductor block. But this metal electrode is insulated from the semiconductor electrode. Now how do you modulate the resistivity of the semiconductor? You apply a voltage between the metal and the semiconductor as indicated in this diagram. So for example, for the polarity of the voltage applied here, it is clear that the metal will be positive and the semiconductor will be negative. So the positive metal electrode will attract electrons. To the semiconductor surface. Now because of this attracted electrons, the conductivity of the semiconductor will increase near the surface of the semiconductor. In other words, we can say that the conductivity of the semiconductor itself will get modulated, it will increase. Now notice that these electrons are being given by the negative terminal of the battery. Now this is the electric field that is causing the change in the conductivity of the semiconductor. So this is the modulating field. If you apply a transverse electric field in this direction using another battery V2 shown here, then a current will start flowing from the positive terminal to the negative terminal. Now this current will depend on the conductivity of the semiconductor. Since the conductivity is being modulated by the metal, the current will be modulated by this particular metal electrode. So in other words, you have modulation of the current by a transverse electric field. Transverse means perpendicular direction. So this was the concept that was proposed to implement the vacuum tube triode in the solid state device using a semiconductor. Now what is happening here? This is the controlling voltage V1. This voltage V1 controls the current I, which is created because of voltage V2 and which is also dependent on voltage V1. So V1 controls I. Now this is what happens in a vacuum tube triode also. There is a controlling terminal which controls the current. And now one can always use this particular device for amplifications and so on. How this is to be used for amplification is a separate topic, but what we want to show here is how a current can be controlled by a transverse electric field, which is what happens in a vacuum tube triode, and how the similar concept can be realized in a solid state. So solid state means a semiconductor is a solid. So that is why this is called a solid state device as against a vacuum tube device, which is created in a tube, a glass tube which has vacuum. So please read up a little bit on the vacuum tube to understand how the vacuum tube triode works. That is beyond the scope of this particular course. Coming back to the developments, people started realizing this device. They found that to make this device, you must have an insulating layer between the metal and the semiconductor. This is where they face difficulty. How do you grow a high quality insulating material which is sufficiently thin so that you can get conductivity modulation in the semiconductor by putting a metal electrode on the insulating layer? So as they started working on the insulator semiconductor interface, they got into more and more difficulties. Specifically, what they found is a practical device which was being realized according to this idea had very little current modulation by the control voltage. So though if you make a simple calculation based on a capacitance model for a certain voltage V1 or a certain change in voltage V1, you expect a certain change in the conductivity by the simple capacitance formula. And then using that change in conductivity, find out what is the change in current for a given voltage. Now that was the expected change in current, but practically the device hardly showed any change in current. This was the problem. Now this problem continued to bog the researchers until 1948. So you can see that 1935 to 1948, this is about 13 years. So many research workers were putting in all their brains to solve this problem of lack of conductivity modulation. In order to study this particular problem, Shockley, Bardeen and Brattain, these three scientists, in one experiment tried to put two contacts in close proximity on the surface of a semiconductor, because they knew that something is happening at the surface of the semiconductor which they wanted to understand, that is responsible for lack of conductivity modulation. So to study the surface, they created some such arrangement, and they were trying to see the currents in these two particular loops as shown here. So this is the semiconductor block, and these are the two contacts in very close proximity. Now what they found when they were trying to measure the currents in these two loops is that a change in current in this loop was inducing a large change in current in this loop. Now they realized that this is some kind of a transistor action that they were looking for. This is exactly what is happening, or what is rather supposed to happen according to this idea, except that here you have a controlling voltage which is modulating this current. In this case, you had a current which was modulating another current. Of course, this current is also set up by a voltage. They immediately realized that this is some kind of a solid state triode that they are looking for. We will see in a detailed discussion why this device was called the transistor. We will understand this when we take up the transistor action in detail. But for now, let us proceed with the developments. So they call this particular device wherein the current between these two terminals was being modulated by the current between these two terminals as a transistor. So they called one of these terminals as the emitter and this one as the collector, and obviously the third one, which was looking like a base on which they had put the emitter and collector as the base terminal. So that is how you have emitter, base and collector in a transistor. So though the action of this particular device was different from this particular device that was proposed, in the sense that here the current in this loop was controlling the current in the other loop, whereas here the voltage was supposed to control the current here, but otherwise the two devices are similar in that one terminal controls the current through the other two terminals. So therefore they realized that this device can be used for the particular purpose for which they were doing the experiments, to perfect the other device, that was the vacuum tube triode given in the patent. So in fact the diagram on the patent looks something very similar to this. So once they found some device which they can use, they abandoned the experiment that they were doing to perfect a device according to this concept, and then they started perfecting this new device which is called the transistor. So it is in 1948 that this particular transistor was discovered accidentally while trying to perfect the vacuum tube triode. Rather the solid state equivalent of the vacuum tube triode. So we can call it the solid state triode. So while trying to perfect this solid state triode, they accidentally discovered the transistor, and when they tried to explain the operation of this device, they found that it is because of both electrons and holes, and that is why they called this as a bipolar device, and they call it as a bipolar transistor. So that is how the name bipolar junction transistor came into being. Bipolar junction transistor, because the operation of this device could be explained using the theory of p-n junctions that had been developed, and the operation of this device involved both electrons and holes, that is why the word bipolar. So that is as far as the history of the bipolar junction transistor. Further developments that took place after bipolar junction transistor we will consider in the context of the MOS field effect transistor, which will be discussed after the bipolar transistor action, and maybe in about 5 to 6 lectures we will try to cover this bipolar junction transistor and then take up the theory related to MOS field effect transistors. So that is the history of the bipolar transistor, which was discovered in 1948. Now we will consider the structure of the device that is there in the modern days, and then we will see how we can approximate the structure for the purpose of our analysis. Let us consider a PNP transistor. And then you can always find out for yourself how you can make an NPN transistor. So you start with a heavily doped p-type substrate, that is a p plus substrate, and then you grow the subsequent layers. Now the details of the processing of bipolar junction transistor are very similar to those of the p-n junction that we have considered earlier. So you know that the p-n junction in modern days is made using a planar process. So same planar process is used to make this bipolar junction transistor. This process involves cyclically going through the steps of deposition of layers, then patterning of layers using photolithography and etching, okay, and this is repeated again and again until the final structure is realized. So that is what is happening here. You start with a substrate which is heavily doped, and then on that you grow a lightly doped substrate of required doping level, which is a p-type layer. Then through a window you create an n-type diffusion, and then through another smaller window you create a p-type diffusion. Now here it is important to note that the doping of n-type region is more than the doping of the p-type region, and the doping of the p-type region is even more than the doping of the n-type region. So this can be shown by a doping profile that can be drawn on this side. So here you have the doping and here you have the distance. We are going to plot this on a log scale. So doping is plotted on a log scale because we want to show a wide variation on a single diagram. So the doping level varies over orders of magnitude, and that is why one must use a log scale to show the doping level. So the doping looks something like this. So you have a heavily doped p-type region. So this is how it goes, and then you have a p-n junction at this point, and then you have a relatively lightly doped n-type region, and then you have a p-n junction again here and a much lighter p-type region, followed by a heavily doped p-type region. So that is something like this. The doping levels would be something like this. At this point the doping level would be of the order of 10 power 20 per centimeter cube. This doping on the other hand would be of the order of 10 power 18 per centimeter cube, and the doping here would be of the order of 10 power 16 per centimeter cube, and back here is again 10 power 20 per centimeter cube. Please note these are the rough values. Depending on the rating of the transistor, these values will change, but definitely this gives you an idea of the order of magnitudes involved. Now what about the distances? So taking this as the reference point, here this could be about 2 to 3 microns, this point, and this point, if this is 2 microns, would be 3 microns or less. So the distance here between these two junctions is about a micron. These are the two junctions in close proximity. So p-n junction here and this n-p junction here, which are responsible for the transistor action. So here the distance is in microns. Now this point here will depend on the breakdown voltage and other requirements of the transistor, just like in a p-n junction. So it could be, for example, about say 10 microns. It could be more or even less. And of course the thickness of this substrate, as you know, will be more than 100 microns, because this thickness is decided by the mechanical handleability considerations for this device. Now here this is the silicon dioxide layer, in which the windows are created to create this p-n diffusions. Now this is the cross section of the device. This is the PNP transistor. The top view of this device would look something like this. So these three show the metal contacts. So on this, when you want to take the metal contacts in a cross section, they will look something like this. And these contacts are what are shown here. So this is the emitter contact, and these two are the base contacts, because this is the base region, and the collector contact for this particular transistor is at the bottom. What we are considering here is a discrete transistor. In an integrated circuit transistor, on the other hand, the collector contact will also be on the top, somewhere here for this particular region. For a discrete transistor, it is at the bottom. We will consider the discrete transistor here because its structure is simpler. So you have that contact at the bottom. This is the collector. So let us draw this emitter here. So on the top view, this is the emitter and these two are the base contacts. So that is the structure of the device, the real structure. Now as we have been saying, for the purpose of analysis we need to use a very simplified structure for which simple equations can be derived and the essential phenomena can be very clearly brought out. So for the purpose of analysis we are going to use a one-dimensional structure which looks something like this. So we are going to assume a structure that is obtained if you just take this portion of the device. So as you can see here, if I were to separate this portion, it would look something like this. I have the P region, then I have the N region which is very thin. So this is the so called N region that is being shown here, and then I have the again P and P plus. So if you want to show the relative doping levels, then probably this should be called N plus and this should be P plus plus. This doping is more than this doping is more than this, and this is more than that. So P plus N and this is P and this is P plus. So this is our device, this is the emitter, this is the collector, and the base contact we will show on the side. As you can see here, in real life you cannot really connect the base contact here on the side as shown here. This base contact will be in the same plane as the emitter contact. But for the purpose of analysis we are showing an idealized structure with the base contact on the side. Further, what we will do is we will ignore this P plus layer and we will assume our collector contact is right there. So this will be our idealized structure of the PNP transistor. Now in the real transistor, the current flows from the emitter to collector. So that flow we can show as something like this. But you can see that you also have flow on the sides. So really the current flow is two-dimensional in the real transistor. Further, if you see the current into the base contact, so that current is flowing sideways, it flows like this. So this is really a rather complicated situation, which is being simplified here to show that the current is almost entirely in one direction. So this is a one-dimensional approximation, and you do have a base current flowing from the side, but its effect will not be considered in our analysis, meaning that we are going to consider the effect of the base current definitely, because without base current you cannot have this current flowing. As we will see, the base current controls the current between emitter and collector. But what we are saying now is that the lateral flow of the base current effect of this we will not consider in a simple analysis, and later on we will show how you can accommodate this effect also. So our analysis will be based on this particular idealized device structure of a PNP transistor. So doping in the emitter region, this is called the emitter region, this is called the base region, and this is called the collector region. So doping in the emitter region is more than the doping in the base, and the doping in the base is more than the doping in the collector. So we could probably show this as follows. So P plus plus N plus P, or alternately we could also write as P plus N P minus. So it all depends on which way you want to represent. Basically we want to emphasize that doping in emitter is more than that in base, which is more than that in collector. Now although the NPN transistor is more often used than the PNP transistor, because the electron mobility is more than the mobility of holes. So the NPN transistor is faster and it can carry more current for a given voltage conditions than a PNP transistor. Still, we use a PNP transistor to develop the theory. The reason for this is as follows. In a PNP transistor, the current is because of holes moving from emitter to collector, and you know that for holes the direction of the current is the same as the direction of the movement of the carriers. Now, as we will see, in a bipolar junction transistor the current is because of diffusion. So if you consider a PNP transistor, the current direction will be the same as the direction of the hole diffusion. That is the reason why a certain simplification results, because the current direction is same as the direction of the movement of holes. The understanding of the transistor action is simplified. In a NPN transistor, on the other hand, the current will be carried mostly by electrons and the current direction will be opposite to the direction of the flow of electrons. So because of that, some minor complications arise which can be avoided while developing the theory for the first time. So this is why the PNP transistor is considered for explaining the theory. Now, when we discuss the transistor action and other aspects of the transistor, we will draw the transistor in the horizontal direction like this. So where this is the emitter, this is the base, and this is the collector. Now, apart from the simplification that we have already considered for the device structure, one more thing that we will note is that though actually the doping profile is highly non-uniform, and this non-uniformity of the doping profile does have an effect on the bipolar transistor action. However, the basics of the transistor action is not due to the non-uniformity of the doping profile. So therefore, in our first analysis, we will assume the doping to be uniform in each of these three regions, meaning that the junctions are assumed to be abrupt. So if the doping profile is shown here, it would look something like this. We will show the acceptor type doping on the negative side, simply because in the space charge region near the junction, the acceptor type doping leads to a negative space charge on the p side. So let us indicate the doping here. We will call this the emitter doping and represent it as n suffix e. Now, the base doping is similarly uniform, but it is much less than the emitter doping. From your doping profile we can see that it is at least 100 times less than the emitter doping. So it will be 50 to 100 times less. So what we need to do is, we need to use a different scale for the base doping and for the emitter doping. So we show this by showing a cut here, because we are drawing the doping on a linear scale. That is why we are able to show the polarity. So here it can be shown something like this. So here also we will show a break, and this doping is NB, the base doping. It is understood that if it is a PNP transistor, the emitter doping is acceptor type while the base doping is donor type. Similarly, we come to the collector, and here the doping is even less than the base doping. So this is shown something like this. So this is this point. So this is minus NC. Now, another thing we need to understand is that the P++ and P regions will be assumed to be sufficiently long for the development of our simple theory for the transistor. Similar kind of assumption we had made in the case of p-n junctions. Now, one critical parameter, distance parameter associated with this particular device is what is called the base width. Now, if you show the space charge region here, let us assume some bias conditions for this transistor. In the simple case, we can assume that equilibrium condition. Let us assume equilibrium condition. So, under equilibrium condition, your space charge region can be shown something like this. So, the space charge region is more on the n plus side than on the p plus plus side, and similarly it is more on the p side than on the n plus side. So, something like this. So, this is the space charge region. Now, the electrical base width is the distance between these two space charge edges. This is called the base width, WB. And similarly, the distance between the metallurgical junctions, this will be denoted by the symbol WB prime. As we will see, it is this WB that is of interest to us for developing the characteristics, and WB is less than WB prime because of the space charge regions. So, that is the device structure that we will be using for the purpose of our analysis. In the next lecture, we will develop the theory for the transistor action.